thank you very much. Thank you for the invitation. So this is the title and the authors. I have to say that this is a version of the talk I give in the recent PQ crypto in Maryland, with some updates due to a recent attack. So this is the outline. I will. This is a multivariable, and this is a kind of different system. So I will take a few minutes to explain how this works, because I say it's a completely different multivariable scheme. So, and the scheme is the mathematics in which it's based is in what we call exponential maps. That they are called in algebra. They are used extensively in algebra geometry, and they are called monomial maps because they are given by, you see, you have a matrix with integer coefficient, and then you can exponentiate a vector to the matrix with this formula. And of course, this satisfies that the composition corresponds to the product. That means that if the matrix is invertible, then you can invert the map, and this is what is given in this proposition. So we have a matrix over set Q. We are working in a finite field, so we can. You can the exponent mod with Q minus 1 if they are different from 0. So if the matrix is invertible, what means that the GCD of the determinant of Q minus 1 is 1, then the application is invertible outside of the axis, and the inverse is given by the main. So these are the mathematics that we use for this. Okay, so then, as I say, the public key of DME is a map that is a composition of linear and exponential map. For instance, we present the first version of DME to the first NISCAL in the category Ken category, and it didn't pass to the second round, and also furthermore it was broken. But then there was also interesting proposed attack by Veulens that what they say is just take the version of the map used by Veldesen over F2, and then try to use the decomposition algorithm, but in this case the decomposition algorithm doesn't work. So the new version that we present, the main difference is that instead of having two exponentials, we have more than two. And the reason that we can have 3, 4, 5 rounds of exponential is because we have a procedure also we add to drastically reduce the number of monomials. So the structure is like that. So as I said, the public key is a map that is obtained as composition of linear maps and are exponential. The linear maps are over FQ, and the exponential are over FQ squared. Okay? With this setting, the DME in principle give a trapdoor permutation. So in principle it can be used for encryption and signature. Let's say a RSA type, signature. Okay? We call the resultant scheme the parameters R, N, and Q. So R is the number of round or exponential, N is the number of variable, and Q is the number of the field. Okay, that is a power of 2. In fact, just a few comments. If we compare with a typical quadratic multivariable system of the same signature size, you see the difference. So DME has 8 variables over the field 2 to the 64. Typical of the same size will be 64 variables over the field 2 to the 8. And the main advantage of the DME is that the timing are measured in microseconds. So all the others that we have seen this week, all the other multivariables give the times in milliseconds. This DME gives the time in microseconds, so there is a huge speed factor. But there is now we have discovered that we have there is a security problem. In fact, 2 days ago they appeared, a notification of an attack that I will talk about. Okay, and how to fix it. All right. So as this is a new system, as I say, we will try to explain a little. So the different rounds use an isomorphism between fq to the square and f, the field of q square element, phi, we use all the time. And then we have a combination of linear maps, R+1 linear maps. I think here I fix a number of variables 8. So we have and then R+1 linear maps and R exponential. So this is the system. So there is a we have in this case 4 rounds. It looks complicated, but it's not complicated. You have here, each horizontal round, we have several linear isomorphisms plus 1 nonlinear part. So here is the nonlinear part. Let's see. So this column is the nonlinear part. And, so it's relatively, it looks complicated, but relatively easy. In fact, sometimes people ask me, how is so fast? In principle, not only fast, it's very simple. They use only linear maps, matrices, and exponentiation. So I say that one way to say that they use only high school algebra over a finite field. So you really can do a lot with high school algebra of a finite field, just exponential and matrices. Okay, so all right. Then so this is really the core, and then a few words how to get the public key. Well, as I said before. We work over FQ or over FQ square, and then if we are here over FQ square, we have a typical element in one of the rounds. Then we can express this in a matricial way. This MI is the let's see, what is my finger? MI is the matrix of the exponents, CI is the matrix of the coefficient, and 1U is the base of Q squared over FQ. And then, because the exponents are a power of 2, is easy to get this formula. And in particular, in order to get the final polynomials, the way to do is very fast. Using this matricial expression of each component, we see that finally the matrix of the product is just for the monomials, is the Kronecker tensor product of the monomials, of matrix monomials, and the same for the coefficient. So really, this is really going very fast. All right. Well, there is also the other important thing is reduction of monomials. I will be quick here, very quickly here. You have one of these exponential matrices has one exponent common in both parts. Then we can just having this linear expression in the exponent. In the second exponent, we can produce two equal monomials. In fact, not only two equal monomials, but a lot of them. So you can see here one example. We apply this with only two linear conditions in the exponent. We can pass, in this example, from we can apply only the second and the third exponentiation, not in the first, because and we pass to the principle from the final number of monomial to the 7, to the 7, to the 6, to 30, 32, 36, 34. So there is really a huge reduction of monomial. Okay, so, and then the result that we can produce, remember that in every step of this composition, the linear part are isomorphism, and the nonlinear part are also a bijection in the FQ minus the axis. So what we have is that we don't have a fine translation, then the public key map is a permutation. Okay, and if we have a fine translation, then there can be failure of decryptation, or failure of signature, but the failure of signature can be always avoided. So as I say, this is a permutation we can use for chem and signature using the standard padding that can be they use for RSA. So OAF for chem and PSS for signature. And these are very well studied, so the security is very well known, and the system is secure if the central permutation is secure, of course. Okay. So, and then one comment is that even if we put some affine translation, then it's possible to get rid of invalid signature. Yes, we have to make the inverse of all the elements is the inverse we have to apply. So L minus 1, 3, F minus 1, etc. And if the problem is that with the affine translation, it can be some zero can appear, but if this happens, then we can start again. So we start again with another padding. So these invalid signatures are always easy to avoid. All right. So we will talk about a little about security. Our main concern, or let's say principle, are this kind of let's say of attacks, if you like, of possible attack. Then first is well-designed grounded basis attack and structural cryptanalysis. So as I said, well-designed, that means that just we take the polynomial over FQ and then convert it in polynomials over F2, all right? And I say there was proposed by Bailons to apply the composition algorithm of Fourier-Perret. But this algorithm works only for generic. So the algorithm just works that you have a composition of two polynomials, for instance, quadratic. You get a quartic polynomial, but as I say, over F2. But it works only for generic polynomials. So for a special, that's we check in. But anyhow, we decided to increase the number of rounds, because increasing the number of rounds increase the degree of the final polynomial F2. So the final polynomial F2. So this is the main reason to increase the number of rounds. I mean, this give more security against well-designed. Then the other. The other way that we have to look at, the other is just as all multivariable systems, we can try to solve the corresponding system equation. If we have fx equal to I, we have to make, you can try to solve this ideal and using Grotner base, and then complexity, a standard complexity using a 4 or 5 Fourier algorithm is just given by this formula. Okay, but in this case, SD is the solving degree. I mean, the higher degree that appear in the Macaulay matrix. And then, of course, because we start with degrees of the order 2 to the 64, so the solving degree is very high. So that means that in this case, this setting will give, this formula will give a complexity of 2 to the 1000. Of course, this is an upper bound. One has to be more, I mean, to see really, try to see what is the real complexity. But the problem is that we did a lot of experiment, but only for very small field. The question is that really the complexity go up very quickly. So we can only solve. We use Magma with a relatively big computer with half a terabyte of RAM, and the system can only be solved for 2 to the 4. So 2 to the 5 already solves the. So we would like to have more experimental, but work, but I mean it's not possible. Okay, so if anyone has a computer with a few terabytes of RAM, we can send you some to see how is going this. Okay, and then the structural cryptanalysis. So as I said, I prepared this talk like 1 week ago, but of course I have to change this slide because structural cryptanalysis means that you have you have a public key of a composition of F and L, a linear and non-linear part, and one can start to try to find the last linear, that is LR, and then go back. In fact, we were some estimation, but as you see here, 2 days ago, Daniel Smith-Ton and with other 3 collaborators at the NIST announced K-recovery attack. So, in fact, we have to, I mean, they make the announcement, but we have to check it. We have not checked, but I do believe that this is correct. But we have also a solution. We'll come later. Okay. So, and as I say, I was here, so I didn't check completely, so I cannot give only a few details. The idea is that, of course, the initial map is over FQ to the 8, but then is, of course, with this isomorphic that we use, it can be converted to a math into FQ 4 to a square. So I mean, and in this new map, it really has a very special form. So that's in fact a very special form that this is very simple. Not only very special, but very simple. And this is the reason of the attack. Okay. So, but we'll make a further comment. So, what about the timing? This is the timing of one of the versions, not the one we presented to the NIST, but you see, we compare. We try to compare, for instance, DME with 3 and 4 rounds. You can see the difference. Always for category 5, you can see the difference, and in speed, and you see the main thing is that the signature is very small. This is 60 is the smallest one. So 65 bytes for category 5. The secret key, the public key is not. It's also small. It's just 4,000 bytes or 2,000 something for 3 rounds. Okay, and then you have here the comparison, and then for the NIST presentation we have we present in 3 categories. You see 1, 3, and 5 security categories, and you see that for us the security is just directly related with the size of the field. So and you see that the time is really given in microseconds. So and it's almost and it's really very fast. Okay, and also we say the public key is really for this version is really very small. Okay, so finally, of course, you see this slide and the previous slide that the speed and the size are very good. So we have some space to give more security without a penalty in the speed. Really, we can really give more and then. In fact, this were my last is my last slides. In 2 days ago, there was a question mark. So more security. So we were asking ourselves, we can we can have more security, but because of the attack now is not is an imperative mark. So now we must have more security, of course. And what we can do, for instance, in order to increase the security for the ground basis is very easy. We saw in the previous slide. We just have to increase the number of the size of the field. Okay, for the well descent, we have to increase the number of rounds. And finally, for the structural attack, we have to make just some minor modification. So take away one or two of the equation. So this will make, of course, it will be cannot in this case we cannot use for chem, but we can use for signature. In fact, we have a version. We have even implemented a version that with this characteristic, maybe and that is resistant to the attack because of this minor modification. But I think we will release in 2 weeks. Because first we have to study well the attack and also to study well how this minus version resists. But as I say, in principle, we are confident that this new version that we were already working on that before the attack will be resisting to the Daniel attack. Okay, and that's all. Thank you very much. And if there is any question.